So, dear students, I hope everybody is fine, everybody is doing well, and I'm trying my level, and maybe I fail at times, but I'm trying my level best. So, in this video, I'll be talking about. I'll try to give an overview of the classical description of the free particle, and then in another context of the same video, I'll be talking about the quantum mechanical description of the free particle. So what we say is that, in classical mechanics, a free particle is basically an object. So an object that is not subject to any kind of force. So if you have a particle, if you have an object, and if you don't apply any kind of force on this object, it's a free particle, and it is non-interacting with any potential fields. It does not interact with anything or other forces. The classical treatment of a free particle is it's basically a fundamental concept that certainly helps us illustrate some key principles of mechanics. So let's go with those some basic descriptions of the particle, the classical particle that we have. So we have a free particle, and this free particle is an object which is not interacting at all with anything, and no force is acting on this. So I can say here that this free particle in classical mechanics is described by its motion according to the Newton's laws. And since no external force is acting on this particle, its motion is straightforward. It's going to go straight forward. Because no force is acting on this particle. So this is my classical description of a free particle. So it will keep on moving in that straight line if this particle at all is in motion. Now, if we talk about the Newton's first law and equations of motion. Newton's first law states that a particle will remain, it will remain at rest, or it will continue to move in a straight line at some constant speed, unless there is no external force acting on this particle. So for free particles, so if I write down the Newton's second law, F is equal to ma. F is the force acting on the particle, m is the mass of that particle, and a is its acceleration. And the net force acting on the particle is zero. So if F is zero, we will say that this ma is zero. And what does it imply? What does it mean mathematically? This implies that this acceleration of the particle is equal to zero, because this mass cannot be equal to zero. So this mass is not equal to zero. What does that mean? That means the acceleration of this particle is equal to zero if no external force is acting on this free particle. And since the acceleration is zero, what does that mean now? Acceleration is zero. A for acceleration. Acceleration is zero. The velocity of the particle will remain constant, because what is acceleration is dv by dt. So we can write down the integral of dv is integral of 0 dt. So v is simply a constant. So we can talk about we can talk about this free particle, and this free particle is a particle which is not acted upon by any kind of external force. If that's the situation, if this object is in motion, it will remain in motion in the same straight line forever and ever. And if no force is acting on this particle, then its velocity will be a constant. It will have a constant velocity. Now, if we take an example, suppose we have a particle. And this particle moves along the x-axis. So assuming that the particle is moving along some x-axis with an initial velocity. Suppose it has the initial velocity. Let me take that as v0. So v0 is the initial velocity, and it has some starting position, say x0. So x0 is its starting position. If this is the case, the position of the particle as a function of time can be written. So we can write down the position of this particle as a function of time. That's going to be x0 plus the initial velocity with which it is moving over the time t. So this is going to give us the position of the particle after the time interval equal to t seconds. Now, if I take the value of this x naught, so this if I have some if I have already some position, say if I take x naught equal to say 2 meters, and if I choose this v naught equal to say 5 meter per second, then I can calculate this x of t. X of t is going to be 2 plus 5 times 3, and I'm going to get 17 meters. So the particle after the particle is going to be at 17 meters. If I choose x naught equal to 2 meters, if I choose the initial velocity equal to 5 meters, and if I choose t equal to 3 seconds. So this gives us so I can say that the position after 3 seconds of this particle is 17 meters. Now we can take on another, say for example, we go into the domain of a two-dimensional motion, and suppose we have two-dimensional motion, and for a free particle moving in two-dimensional motion. So if I go with two-dimensional motion, what's that? So if I choose my r as a vector, and this r is the function of time, this r is r naught plus v naught of t, where we understand this r is nothing but, in Cartesian coordinates, it's xi cap plus yj cap. We can take it like this. So here we are talking about two-dimensional motion, and let us have, for the given situation, let us have r naught, because r naught will have two coordinates, say 2 and 3, and the initial velocity will have two coordinates, say for example it is 4 and minus 1 meter per second, and this is certainly meters, and at the time t equal to, say, I'll take 5 seconds here. So what will be r of 5 here in two-dimensional motion? It's going to be 2 and 3, okay, then plus 4 times 5 comma minus 1 times 5. Okay, so this will give us 2, and then plus it will give us 20, comma we will have 3 and minus 5. I'm doing the same thing in 2 dimensions. So finally we will have 22 meters along x, and we will have minus 2 meters along the y direction. So here we are describing the particle classically, and we can locate the position of this particle at time equal to 5 seconds. If I choose its coordinates and 2 and 3, and the coordinates of its initial velocity as 4 and minus 1. And what we have here, in addition to this, is the energy considerations. I mean, we have the kinetic energy of the particle. So we have kinetic energy of this classical particle. And what's that? That's k is 1/2 of mv squared. So m is the mass of this object, and v is the velocity of this object. Now, if this v is constant, why v is constant? V is constant because we are talking about the free particle, and no force is acting on the free particle. When no force is acting on the free particle, its acceleration is 0. If its acceleration is 0, then its velocity is a constant. So we can say that this k equal to 1/2 of mv squared, this energy will remain constant for this free particle classically. And the next thing is the momentum of this particle. Momentum of this classical free particle. So talking about its momentum, we understand momentum is basically it's a vector quantity. It's the product of mass of the object and velocity of the object. And for a free particle, this momentum is a constant. So P is constant. It's constant for the free particle because, as I said, the acceleration is zero, so the velocity is constant. So these are the fundamental views to interpret a free particle in classical physics. And so in order to summarize this thing, what we have tried here is we have subjected our free particle to the classical treatment, and what we have tried here, we have described the particle's motion as the straight line. For the free particle, its motion, if it is in motion at all, it will move always in straight line, and it will have the constant velocity with which it will move. And the position of this particle, the velocity of this particle, the momentum, all of these things being function of time with constant values, and energy being constant over all time for this free particle. So from here, we would like to have we would like to go into the domain of this of the particle, but here we want to talk about this free particle in the context of quantum mechanics. So we will subject the same concept, the concept of a free particle. So now we have free particle in quantum mechanics. Free particle in quantum mechanics. And in quantum mechanics, what we have, the treatment of the free particle is more complex. It's not the way that we talked about the free particle in classical physics. It is more complex than that of classical mechanics. And why it is complex? It is complex because of the probabilistic nature. Probabilistic nature. Probabilistic nature of quantum states. So here we will try to go with some steps to have an overview of understanding this quantum mechanical treatment of this free particle. And we will try to take a note of a couple of examples so that we have an idea about the concept of a free particle in quantum mechanics. So where do we start when we talk about the free particle in quantum mechanics? In classical mechanics, we started from Newton's law. And here we have the basic equation. In quantum mechanics, we have the state of the free particle. And this state is described by what is called as wave function. And it is symbolized as psi of r and t. And this wave function, I mean this psi r of t, what it does basically, it provides the information. It provides the information about the probability of finding the particle, in a given position at some specific time. So the time evolution of wave function is governed by the equation. So we have the Schrodinger's equation. So we have Schrodinger's time-dependent equation for a free particle. So if I have to write the Schrodinger's equation for a free particle, what it is I h cross dou psi by dou t minus or equals to h cross square by 2m del square psi as the function of r and t, psi as the function of r and t. So this is my time-dependent Schrodinger's equation. And this Schrodinger's equation is there for the particle, a free particle. And we better understand the meaning of this symbol. This h cross is it's the reduced Planck's constant. Psi of rt is the wave function, and this is dou by dou t. It's the time derivative of this wave function. M is the mass of this particle, and this del square is a Laplacian operator, and we understand that this Laplacian operator del square is it is dou 2 by dou x2 plus dou 2 by dou y2 plus dou 2 by dou z2. So depending on the treatment of the problem, suppose we treat a problem along x only, so we will have to incorporate only the x portion of this Laplacian operator in the Schrodinger's wave equation. So what we have here, we have I. This I is an imaginary unit. This h bar is the reduced Planck's constant. And we have talked about it a couple of times before. And this m is the mass of the particle, and this delta square is the Laplacian operator. And we have written down this Laplacian operator in Cartesian coordinates. Now, this Schrödinger wave equation for a free particle, it has a solution. And the common, generally utilized solution for this Schrödinger's equation is, so writing down the solution of this Schrödinger equation is that the psi of r of t is a e to the power of iota times k dot r minus omega t. So this is the plane wave solution. This is the plane wave solution for this free particle. And we have some symbols over here. This A is a normalization constant, and we better understand that we can calculate this normalization constant using the condition of normalization, where we have to apply the boundary conditions for the given problem. And this K is called a propagation vector, or it's also called as wave vector. And this K is it is equal to 2 pi by lambda. And then we have omega. This omega is the angular frequency. This is the angular frequency of the particle, and so this is angular frequency. And then we have k dot r here. So this k dot r is basically the dot product of the wave vector k and the position vector. And omega t that we have here, this omega t is the term that's involving the time. So the solution for the plane wave is composed of the normalization constant, an exponential function, and this exponential function is dependent on the propagation vector and the angular frequency of this particle. And we can talk about the wave vector k. This k is the wave vector, and this k is related to the momentum of this particle. So momentum here is this momentum. When we make use of de Broglie equation, we will easily calculate the momentum of this particle as h cross k. So this is the relation between momentum of the particle in quantum mechanics and the wave vector of the particle. And similarly, we can, because omega is the angular frequency of this particle, then we can, this omega is related to the energy of this particle. And what is the energy of this particle? That is, E is equal to h cross omega. And then we have energy and momentum of the free particle. And what is that? This energy is, we can think of 1/2 of mv squared, and we can think of mv whole squared by 2m. So this is equal to p squared by 2m. So if we think of substituting the value of p that we have obtained here for this particle, which is h cross k, and we can utilize this in this equation. So for p, I can use h cross squared k squared by 2m. So, so what we see here, we can even boil down this. We can boil down this to, because E is h cross omega, so I can write omega here, and this h cross will cancel with the square of this, so we'll have omega is h cross k squared by 2m. So this will be the angular frequency of the particle that we have been talking about here, and this will give us the measure of the energy of this free particle. Now, what is important here is that this plane wave solution has a constant which is known as normalization constant, and which is denoted as A. And in quantum mechanics, wave functions must be normalized, because then otherwise it doesn't make any sense. So that the total probability of finding the particle in the space is equal to 1. So if P is the probability, this probability over the entire space that this particle may be present in, this must be equal to 1. And for plane waves, which are not normalizable over all space, we often use the concept, or that concept that's called a box normalization. box normalization. And now, if I take an example, suppose I consider a free particle in one dimension and I write down its plane wave solution as x and t equal to a e to the power of I kx minus omega t. So we better understand the meaning of the symbols here, and we will have this k is the wave number or propagation vector, and omega we can write here for this plane wave as h cross k square by 2m. And to find its momentum, what's the momentum? Momentum is h cross k, and what is the energy? Energy is h cross square k square by 2m. So we have a plane wave solution of the Schrodinger's time-dependent equation for a particle which is free, and it has a momentum equal to h cross k, and it has the energy equal to h cross square k square by 2m. Now we can take another example of, say for example, a Gaussian wave packet. A Gaussian wave packet. Now, this Gaussian wave packet, it's a more realistic representation of the free particle. I mean, a free particle is basically a Gaussian wave packet, which can be thought of as a superposition of many plane waves. So, this wave function we can write down this Gaussian wave packet describing this free particle as psi of x and t is 1 by 2 pi sigma square whole raised power 1 by 4 e to the power of minus x square by 4 sigma square e to the power of minus I e t by h cross. Where this sigma that we have here, what it does, it describes the width. It describes the width of wave packet. And the evolution of this wave packet, in time, what it does, it demonstrates the spreading of the wave packet, which certainly reflects the uncertainty principle. As the wave packet spreads out, its momentum intensity increases. And we have another important principle that's quite oftenly utilized in quantum mechanics, and that's uncertainty principle. And for the free particle, this uncertainty principle can be written as del x del p is greater or equal to h cross by 2. This is the uncertainty principle for the free particle, where this delta x is it is the uncertainty in the measurement of the position of the particle, and this delta p is the uncertainty in the measurement of the momentum. Now, for a Gaussian wave packet that we are talking about here, now this for this Gaussian wave packet, this width, what is that? That's this sigma. This the width of the wave packet gives the estimate of this uncertainty in the measurement of delta x. And the width of the momentum space in the Gaussian wave packet, we have not described that exclusively here, which has been described in some other video. The width of the momentum of this momentum space is inversely related to this sigma. So we can summarize the free particle situation in quantum mechanics as, the quantum mechanical treatment for the free particle. What it involves basically is it involves solving the Schrodinger's equation to find the wave function, and using plane wave solutions to describe the particle's state. And calculating the momentum of the particle and energy from the wave vector k, because k has a clear relation with the momentum, and it has a relation with the energy that I have tried to describe. And considering this wave packet representation for more realistic situations, and applying the uncertainty principle to understand the limitations in measuring the position and momentum of the particle. So these are the foundational concepts in quantum mechanics, and what they do is they are utilized to illustrate how quantum particles behave differently from that of the classical particles.